Hey everybody. In our previous video, we learned how to use the calibration tools in GMS to import uh, observed head data from monitoring wells as observation points in the map module, and also to assign field observed flow values, or for example discharge to a stream, either gains or losses for flow between a river and an aquifer, and then how to run mod flow and get calculate residuals. That is, compare the model simulated values at these observation locations with what we observe in the field, and then how to display the various error norms that show how well calibrated our model is. And then we talked about trial and error calibration. So in this tutorial, we're going to use those tools again, but this time we are going to do what's called automated parameter estimation, and we are going to run a utility called PEST that takes some information that we provide it in terms of what parameters to change, and then it runs mod flow over and over again, and it changes the parameters until the model output matches what we observe in the field as best, or the best it can. So it minimizes our total error on the model. And so this is a great tool to use for calibrating your model. I generally recommend that you do trial and error calibration first, but this can be a really powerful tool. And so let's get started on it. So the first thing we're going to do is open our Big Valley model, and this was downloaded from the Acquaveo website. It's a zip archive called inverse.zip, and when I unzip that, there's this Big Val model, which is the same model that we saw before, and we have our calibration targets shown here. Let me expand my Project Explorer window. And we also have a flow observation. So we have both a flow observation and a set of head observations. And we have a set of hydraulic conductivity polygons and a set of recharge polygons that we're going to be working with. And so the first thing we're going to do is parameterize our model. We need to tell, we're going to use this optimization utility called PEST, P-E-S-T, and for that to work, we need to tell it what parts of our model input to change. And in GMS, we do that using something called a key value. And for example, let's look first at our, I'm going to turn off some of these other coverages here. So this is our hydraulic conductivity coverage. And right now, if you look at the attribute table, each one of these has, let's see, polygon. Yeah, they all have a hydraulic conductivity of 2.4. But we want PEST to, we can use that as a starting value, but we want PEST to control each of these independently. And so in the tutorial instructions, it talks about these key values. And the idea is we enter some numbers in those in the hydraulic conductivity array that represents values that you wouldn't normally see in your input. And so a good way to do that is to use negative numbers, because you don't normally have negative hydraulic conductivities. That wouldn't make any sense. That would make mod flow crash. And then we'll use these key values to index our parameters later on. So using this as a guide, I'm going to use the select polygon tool. I'm going to double click on that one, and it will be -60. And then this one will be -30. And then these two right here, I'm going to hold down the shift key to multi-select. and then open that up, and these will be minus 90. And then finally this one would be minus 120. You want your key values to be unique, so use a different one for each polygon. And the next thing we're going to do is set up our recharge zones, and we have a set of numbers to assign there. Continue with the same approach of using negative values. This one will be minus 150. We're going to override our initial values. These two here will be minus 180. And this one will be minus 210. Okay. All right, it's as simple as that. And then the next thing we need to do is go to the Feature Objects menu, select Map to ModFlow. And what that does is that copies all of those changes we made over to the ModFlow input arrays. So if you look here, this is hydraulic conductivity. We have minus 30, minus 60, minus 120, minus 90 somewhere. Yep. So those have all been assigned. Our recharge values, likewise. We've got some of the original values up here in the top. That means we're not going to parameterize that section, but everything else, we have these key values down here that we're watching, or that we've assigned. And next thing we're going to do is we're going to go to the ModFlow menu, go to the Global Options package, and over here it has these things called Run Options. Thus far we've been doing what's called a forward run. That's when you input the parameters and it outputs heads and flows. We're going to switch to parameter estimation mode. This is sometimes called inverse mode, and in this way we're going to provide as part of our input the observed heads and flows, and it's going to solve for the parameters for us. And that actually turns on pest for us. And then another thing we're going to do, I should have stuck with that for a second, in the Global Options package, we need to look at our starting heads. A good approach to use for your starting heads when you're doing parameter estimation mode is to take your computed head values from a forward run and copy them to your starting heads array. And we're going to do that by using this 3D data set to grid button. And we're going to select our solution, copy that in. It looked like that had already been done for us, so it didn't change anything. So what that does is and normally we have the starting heads equals grid top elevations. You'll notice that's turned off. So what this does for us is it makes it so our starting heads are closer to the final heads. And for a small model like this, that's not going to make much of a difference. But for a bigger model, that can make your model a little more stable. But it also, if you're going to run your model, you know, hundreds of, maybe thousands of times, if you can shave off a few seconds each time by having your starting heads closer to the solution, that can save you a lot of time in the long run. So that's why we do that. And okay, we'll save our changes there. And we need to go to the ModFlow menu now and select parameters. And we're going to click on this button that says Initialize from Model. And what that does is it searches through our inputs and it looks for negative values where it wouldn't normally expect negative values. And you'll notice by doing that, it's found each of these key values that we entered for hydraulic conductivity and recharge. And so that properly sets up our list of parameters. Now these are the things that we want to pest to change. So we also need to give it a set of initial values, and then min and max values, and then whether or not we want it to be log transformed. And so let's go in and I'm going to, over here in the tutorial, you'll see that we have this table of suggested starting parameter values and recharge values, and then min and max values for each. So the hydraulic conductivity, we're going to let it vary from 0.003 to 30, and recharge from a really small value, almost nothing, up to 0.0001. And so I am going to cheat here, and I'm going to select that entire table and copy and see if I can do this. Nope, it's not going to let me do that. All right, let me cancel that. I'm going to have to type these in one at a time. So let's try that again. So I'm going to do 1.2. I thought I could copy and paste those, but maybe not. 0.6, 0.2, 0.001, 0.8, and 6. Okay, minimum value 0.003, maximum value 30. Let me see if I can do this. Copy that down. Oh, there we go. Save me a little bit of time, and these will be 1. There we go. So we have our set of, so again, these are the starting values that we'll use initially to run the model. And these are our min and max values. Now, typically, these starting values come from some trial and error calibration that you've been doing. And you want to give it a good starting value. Furthermore, if you don't give it a good starting value, or when you do give it a set of starting values, you might fall into a local minimum. And so when you're doing automated parameter estimation, sometimes it's useful to vary, to do the parameter estimation multiple times with different sets of starting values. And then finally, this last column is log transform. You generally want to do that for your hydraulic conductivity. That is when it, as PEST is scaling, changing the K values, it does that on a log scale. And if you're doing log scaling for hydraulic conductivity, it's not a bad idea to also do log scaling for the recharge as well. So we should be good to go there. So we'll change that, save those changes. And finally, one other thing we want to change, we're going to go into the PCG solver package, and we're going to up our iterations to 100 and 100 for a max number of inner and outer iterations. And that just ensures that you want to make sure that when it's launching all of these mod flow simulations that they all converge, and so by upping the number of iterations, we give it a better chance to converge on us. Okay, so now let's save this one last time, and now we should be able to run this model. And when you run in parameter estimation mode, up on the right you have a list of PEST iterations, and then each row is a PEST iteration, and each column is a parameter. So that first run has the initial parameter values, and then these subsequent runs represent how those parameters are changing. And for every PEST iteration, it runs, if we have, like, what do we have here, about 8 or 9 parameters, it will run twice for each parameter, so run about 18 times. And then it will calculate the, and sometimes it'll run once per parameter and sometimes twice, depending on the iteration. But in any case, at the end of each time it's run the model for each of those, it calculates a gradient and adjusts the parameter value. And in so doing, it calculates a new error. So this error in column 2 is the sum of the squared weighted residuals. And this is what it's trying to minimize. And you'll see after 7 iterations, pest iterations, it's minimized that. It started out at 5,489, ends up at 25. And so here's our solution. It's modified each of those input values. And this is a really small model, so it goes quickly. That's not always the case. But let's go look at our results. Here are our residual errors. Here's our, we've got green everywhere. We've got a little bit of red right there, which is a little surprising to me. I kind of expected that to be green too. But the residual is only 0.9, so that must just have a small calibration target, because that's a pretty small error. And if we go in here to the right click and look at the attribute table for this, you'll see these are all very small errors. The biggest one is 0.9, and that's not very big. These intervals are all really small. That's why that's red. So the interval is 0.46, and that ends up showing up as outside the range, but it's still a pretty small error, less than a meter off. And let's look at our, if we use the select arc group tool, we'll see that the simulated flow minus 4600, observed flow minus 4644, just off a tiny amount there percentage wise. And if we go look at the properties here on the solution, you'll see we have mean residual negative 0.1 meters, mean absolute residual 0.31, root mean squared 0.4, and then sum of the squared weighted residuals 25. These are all very small values. Now again, this is a small model, not too many observations. You wouldn't normally expect it to go this fast or to calibrate this well, but this one works out great as a sample problem to illustrate that, how this whole process works. Finally, a couple other things we can do. Suppose now you say, okay, I like that solution, but how do I convert this to a predictive model? In other words, how do you take those optimal parameter values and load them in so that I can then do a forward run? And this is how you do it. You go to the parameters dialog, you select import optimal values, and select the .par file that's output by pest, and you'll see this set of starting values now have been changed to the optimal values that were found. And then if you go to the global options dialog and select forward run, if you save and run that, you're still using the parameters, but we'll plug in those values you've defined and just do a regular single instance mod flow run with those, and then you can go on to use your model in a predictive sense. Finally, there's another kind of plot that we might want to generate to evaluate our output. So I bring up the plot wizard, select parameter sensitivities, and then click finish. And this, based on the solution we have, this plots our scaled parameter sensitivities. And you'll see that the most sensitive parameters were recharge 150. Now let's figure out where that was. And that would be, this is the recharge 150. Now it would make sense that that's most sensitive because it's a really large region. It covers a big part of our model. So that's going to have a big impact. And what else do we have? Recharge 210 is pretty big impact. And then hydraulic conductivity 30 HK30, which would be this zone right here. Again, that covers a big part of our model, so we'd expect it to have a big impact. What things have very small impact? HK60, the hydraulic conductivity right around the river. And the reason for that is whenever a river or these river objects with the river package, they're kind of like a fixed head boundary condition, and so the head in this region is going to be controlled very strongly by that river. And so you can change the hydraulic conductivity there. It's probably not going to change the solution much, so that makes sense. And then HK 120 doesn't have much of an impact. That's on the extreme south end of the model, so that's the water is flowing from south to north, so that probably doesn't make much of a difference. And then yeah, those are the two that have the least impact. And so that all makes sense. So it's useful to look at these sensitivities, and you can learn some interesting things about your model by doing that. And so that's pretty much it. As you can see, once you have a model set up with your field observed values, converting that or parameterizing the model and then running PEST is a pretty easy thing to do. And it's just a really powerful tool. Now, PEST doesn't always converge this quickly and this well. It's more common with a real model that you get your answers back and you may or may not get a good fit, and so you try adjusting how you parameterize your model, maybe your starting parameter values, and run it again. But in the long run, it can really save you a lot of time and give you a better fit calibration than you could do using manual or trial and error calibration. Now, that concludes this tutorial. In our next tutorial, or this video, in our next video, I'm going to show you another way to parameterize the input using pilot points, and so we'll be using PEST again.